Hello and welcome back to the Hyperthesis episode 72, the second episode of the sixth season. And again, today we also have a very special guest, Nathan Eddy. My name is Pheely.
I'm Patrick.
I'm Liam.
Yes, I'm Nathan.
All right, so yeah, today's special guest also my colleagues at Queens. So Nathan studies, well, he does experimental studies of nanoscale electronic and mechanical system at very low temperatures, not ultra low, very low. So a little bit about Nathan. Nathan completed his master's of mathematics for teachers degree at the University of Waterloo and received his teaching and science degrees from Brock University. And after teaching high school and math for a while, he decided to pursue his PhD. So now he's doing a PhD at Queens here, studying nanophotonics material and doing fabrication stuff. I think that's my extent of understanding what you do. And I heard that you're building a quantum computer per se in your, at least in your group is.
Not exactly, but similar. We're working on something that may one day become part of a quantum computer.
Yeah, you have like a little skeleton of a quantum computer in your lab.
Yeah. Oh, yeah. So we have a dilution refrigerator. That is definitely true. We have two. I think we have two dilution fridges, and one is currently one will be operational. The other one, I'm not sure what its state is at.
For an untrained eye, when I walked in, I was like, oh, that looks somewhat like a quantum computer. But anyways, so to begin today, I have to start with the intro topic. So I saw this new development. I don't know if it's even new. Well, it's been around for a while now. The new material, quote unquote, it's called the aerogels. And one application I looked at is the application on insulation, that people try to find insulating material, heat insulation, and aerogels been used, I think, in the 21st century as the material that does the thermal insulation. So, what is aerogel? Because when I first heard about the aerogel, is that basically they're air. They just solid air or something. That's when people speak about it colloquially. But really, what is? Can you actually make air solid? Well, it turned out they don't exactly make air solid. They're just trapping air. So aerogel is basically a porous material, highly porous material in its microstructure. Could be in like micro and nano scale, where 85 to 99.8% of the volume is air. It's basically a lot of like these skeletal like fibers that have pores in it, and it's just trap a lot of air. It's like necklace like network that kind of loosely packed and bonded particles of fiber. So most of it is air. And so this unique layout of aerogel basically make it the lightest solid material. It's basically around 0.16 milligram per cubic centimeters. Well, for comparison, water is about 1 grams per cubic centimeters in density. So it's like thousands of times less dense than water. And it has the second best thermal insulation properties after vacuum insulation panel. So as you can kind of guess, they can use these aerogel in, let's say, construction or walls, lining, and such to really insulate the outside world, or thermally insulating, because apparently air is pretty good insulator. So since the early 90s, aerogels was basically thought as the miracle material of the 21st century. Basically, one of the top 10 most promising themes of investigation in science, and they think they could change the world. So a lot of these aerogels are what we call the nanoporous materials, and it could be organic or inorganic material that build a framework that support this kind of porous structure. And the size of the pores is usually around 100 nanometers or smaller. So, and to fill those little pores or little holes, could be air. And and it can be bulk material or even membranes. And there are actually different ways to call the aerogel or the these kind of nanoporous materials depend on how you build it. It could be aerogel, xerogel, chirogel, and or hydrogel. And I don't know much about um, aerogel. I heard about it. I was interested in it because I saw I saw like there's a few companies that try to make like a winter jacket out of the new aerogels. Like I thought aerogel was, when it's you see in the scientific magazine or something, it's like really brittle. It looks like trapped air basically. But apparently, you can make it using other fibers that are highly porous, and it can be very thin but very insulating. So you can have, let's say, look like normal windbreaker jacket or normal like fall jacket, but it can withstand up to like 20 minus 20 degrees Celsius or up or even lower, and it looks like a normal jacket. But I think one of the problem with aerogel would be like it wouldn't be breathable, right? If it's really highly thermally insulating, but it won't really be breathable. So yeah, the aerogels basically can be made of a lot of things, and there are multiple ways to synthesize it. So you can basically a lot of big techniques of drying, either be pressure drying or freeze drying material, so it's very porous. And I think after about 2014, 2015, they start 3D printing these kind of silica aerogels that, well, was made from silica. And apparently you can get really high density or high porosity. There are a lot of pores in there. And you can use it in like medical kit or even in a roofing business to do the floors, water heater, insulating for like high speed train furnace. And NASA even used aerogels to lie their spacecraft or like spacesuit because it's really insulating.
Yeah, there's a lot of good YouTube videos on aerogel, and the ones I'm thinking of are probably old and out of date. So I imagine there's a lot newer ones that have come out, because even way back when it was kind of new, I remember watching some YouTube videos on it where, a guy holds, maybe it was Veritasium, I don't know, but a guy holds like a brick of aerogel, and then he tries to blowtorch his hand through it, and he can't even like feel the heat. He can feel it coming around the aerogel, but not directly on his hand. And he like coats his arm and then dips it in a pool, and it's completely hydrophobic. And you can just imagine there's so many applications for it right away. So I bet there's a ton of them since then that people have come up with.
I do just want to mention for aerogel specifically the method in which they're made, because it's very interesting. And so for aerogels, a great example that I heard is that when you leave, for example, Jello out, that's kind of like a similar structure where it's this polymer chain that's encompassing some sort of liquid. In the case of Jello, it's gelatin wrapped around water. But when you leave it just to dry out normally, it gets really cracked and crusty and all of that. So they use something called supercritical evaporation, where they get that fluid out of the aerogel by putting it into a supercritical state. So at the point where it's not really liquid or gas, it's kind of just a fluid. And then by evaporating it through that process, they're able to get this really nice porous structure instead of
perhaps I should
like weak old
jump in
Jello
here and add
kind
on
of
to that, because
texture.
I do a bit of this in my work. So if you want to supercritical dry something, it's super important to be careful with how you do this process. But the point of it is we often neglect the strength of surface tension. Or there's just that, if you've ever seen water, You can sit it on a penny. Like it's got that nice dome shape. So those hydrogen bonds are actually quite strong. And the surface tension of the meniscus is actually really strong. You can have a spider stand on a still piece of water, right? But these structures, as they're drying, that capillary action of the meniscus traveling along is strong enough to rip apart all these different types of structures. So I do a lot of work with atomically thin materials, and for us, when we're making devices out of them, what happens is, okay, if we want to, work with the different resists and stuff that we use in the nanofab facilities, great, but we have a real problem where we can like rip these structures if we're not careful. So what we have to do is supercritical dry them. So what that means is we put these things in a special chamber called a bomb. And we then flood this chamber with liquid CO2. Now that chamber with liquid CO2, we fill it up and we use that as a solvent to dissolve whatever we, or maybe we used a solvent previously, but whatever solvent we used previously is now miscible with the CO2, so that the CO2 will rinse out whatever solvents are there or anything that we need to remove. So the CO2 acts as you would say, like water when you wash your dishes, sort of thing. Like you add that little bit of soap, you put some water in, it helps dissolve the soap away. But we're using liquid CO2 to do that in this giant chamber called a bomb. And what happens is when we sit there and you let it rinse, you can remove all the other solvents until all that's left is liquid CO2 and everything's submerged under CO2. Now what we can do is if we keep that chamber filled at just the right amount, we can then turn up the heat. And by turning up the heat, what happens is the liquid CO2, which is under high pressure already, it wants to be a gas, but it's under higher pressure. As we heat it, the pressure increases, and it goes past a point which thermodynamically is very important called the supercritical point. And this is going to take it to when, we all know that a gas is technically a fluid, but it's not a liquid. It doesn't have that defined volume. But when if you're taking a StatMex course, there's a point for a lot of these materials where the gas and the liquid phase cease to be different from each other. So what we can do is we can take a particular liquid and heat it when it's up past its critical point. And what happens is it changes, then that meniscus starts to slowly spread out until it's no longer visible. And that's a sign that what you've done is you've created like a supercritical fluid. So what we've done there is we've got a state where this gas is no different from a liquid, or the liquid is no different from a gas. That meniscus just stretched out and it's this sort of high pressure gas liquid. And what we can do then is very carefully, without lowering the temperature, but very carefully lower the pressure by allowing the gas to escape very slowly. And if we're careful, what happens is the gas will very slowly lower the pressure. Because the pressure lowers, we've gone around this point and it never actually liquefies again, but just releases as a slow leak as a gas. If you're not careful, you get condensation and it tries to liquefy. But anyways, by doing this, you can essentially remove all the liquid in the chamber and very carefully allow through like an evaporation, but without any meniscus ever passing any of the structures. So yeah, it's actually not just a trivial thing. It's actually quite a complicated process, but it's really cool. And it's something that thermodynamically is something impressive to really see.
Sounds like I wonder who came up with that, because it sounds like it doesn't sound like a trivial thing to have figured out. It must have taken a lot of great effort.
Well, I think the most of the, we talk a lot in our podcast about, they just do this, But I think last episode too, when Wyatt explained that, they had to do this laser cooling, they had to do this stuff to get to that temperature. When like Liam studied ultra cold atoms, and to get to the ultra cold temperature itself, that process is extremely difficult and involved, right? And even this, like, it's good to have experimentalists in the room, because like, they know they know what's the process of this theory that we read of, or like the process to read of, what could it involve, because it's easy to say, just supercritical evaporate it, or just freeze dry it, but to in kind of modern science, the complexity that we need the material to go to have, or the specificity. Like we need a very specific type of material, and you need a very specific process to get it. And I was thinking about other thing about aerogels, like why is it so insulating, like in heat wise? And I was thinking about the heat equation, and also like diffusion and such, because there are multiple ways to transfer heat, right? Convection, conduction, and radiation. And with, let's say, with a normal wall, convection wouldn't be able to do it because it won't go through the wall, right? And conduction is, well, we have to have the material to it, and radiation is really hard to stop anyways. But if you think about our, let's say, our differential equation course, we definitely, one of the first equation we did was the heat equation, and the diffusion equation. And imagine you have a lot of change in the medium, like the porous material, right? You go from the fiber or the material to air, and material to air, material air. So I think that's make the diffusion of the heat or the transfer of heat really difficult.
Yeah, I mean, I think it's like when you build a house, and if you have one wall, it's not going to insulate heat very well. But then if you have two walls with a gap between them, that'll insulate heat better, because that gap of air between the two walls increases or decreases how much heat you lose. And then you put insulation in, pink cotton candy fluffy stuff that creates all these little gaps, these mini little walls of air. And I think aerogel, I mean, maybe it's a really oversimplified way to think of it, but it's probably just really good insulation.
Yeah, I wonder if it's acoustically insulating too, right? Because well, if it's that much air, that might not be a problem for mechanical waves. So I guess we have to look on that, because, but I don't think, I never heard of people use aerogel as acoustic insulation. But I think people do poke holes in things, right, to make it more insulating, or maybe that's not true. But because all the insulating materials back in the days, the walls in the recording studios had a bunch of like a weird shallow holes in it. Maybe it's the design thing. Maybe it's just to disperse the kind of wave front a little bit of the mechanical wave.
It might have been for reflection. Maybe if you have those holes, the sound doesn't bounce around as much, so you don't get like reverb effects in your microphone. I don't know.
Yeah,
I know
that could be.
I know they have like those foam things they put on the walls now for that, and those are like porous materials. I think like they absorb sound instead of reflecting it.
Yeah, that could be. But I think we should get on to our main topic, which is going to be Nathan. So, Nathan, I think I think you are the first guest that doing your graduate degrees with children, and you got multiple. So, well, I think chat about that at some point. But uh, first, we want to get into your work a bit. So you said you work into the kind of nanomaterial stuff, which remind me of the kind of Metal Gear Solid nanomachines kind of meme. But when people hear about nanomaterials, I think is hard to grasp a little bit, because like nanoscale is on the scale of like molecules and stuff, or like a crystalline structure. Can you tell us a little bit about what you do, and especially what is nanophotonics? Because nano is small, photon is even smaller than nanoscale, but I think photonics mean different thing. Can you explain a bit about your field?
Yeah, so we're actually currently working in a really interesting intersection. So we work with sort of two domains that we're sort of trying to bring together. One of those is mesoscopic devices. Just they're these micro or nanoscale size things but they're sort of in between, and we're trying to look at some of the larger, like, can we bring quantum behaviors forward to sort of larger objects, right? So think of it as like, you could obviously have quantum behavior and some really really tiny thing that's like really hard to detect, but can we make it into a larger system? Can we make these systems that you can sort of semi-observe them, right, with like a microscope even or something? or maybe through maybe it's a slightly larger type of mechanical oscillator that if we run it with a radio frequency signal, it can produce something we can observe. But this is now a macroscopic object essentially because you can view it with a microscope versus say something that is only told it's there due to the math, right? But we also look at something called 2D materials. 2D materials are a really interesting new field because they're atomically thin materials that grow in these planar structures, and they're only really held together due to their van der Waals forces. So that's essentially in the layer they got these strong bonds, but in between layers you just have these really weak van der Waals forces sort of connecting them sheet by sheet. And you are probably familiar with them already because graphene is such a material. So 2D materials are things like graphene, hexagonal boron nitride, molybdenum disulfide, niobium diselenide. These are really cool materials that form in sheets. And what we can do with them is we can take a bulk material and remove some of the layers until we get down to these atomically thin layers. And then what we have is essentially a macroscopic, say, in 2 dimensions, but something that's very nano-sized in that last dimension, because sometimes they're only 1 layer thick, and that can be, 0.3 nanometers thick. That's about an atom. So you can't get much smaller than that before things start to get a little more intense, right? But this is, the limit of atomic thickness is essentially what we're looking at. And this is a really neat laboratory to see if there's more things we can do. How does the physics work? What happens when you get down these limits? So one of the things we've been working with is, like I've worked with is mechanical oscillators and trying to develop these systems where we've got, little drums or trampolines. And if you look in the literature, some years ago, there's a guy named like John Teufel and there's some other groups, but they've made, these mechanical oscillator drums from aluminum. They've been able to like bring them down into a quantum ground state. Or another group recently was able to make a squeeze state for a mechanical oscillator and give it such a millisecond coherence time. And these are really impressive experiments. But I think about 2 years ago, all the rage in one of the physics magazines was somebody was able to construct 2 aluminum drums that were entangled with each other. And these are large under a microscope. You still have to see them, but they are large because they're many micrometer in diameter aluminum drums that were entangled with each other. They've entangled the motion. So they've got these macroscopic objects because you can still see them, but they're in quantum states. That's pretty crazy. So that's one facet of our work.
What temperature were they working? Is it like, how cold is it?
So to get these mechanical oscillators to these quantum states, we're at fairly low temperature, like 30 millikelvin. And even then, we have to do special driving techniques like sideband cooling to essentially remove phonons from the system and try to promote them to their resonant frequencies to essentially cool them further.
Do you work with like ultra cold temperature, like millikelvins too, or more like?
So these dilution fridges go down to about, I think about 30 millikelvin pretty easily. Well, not easily. There's a 300 millikelvin, and then it goes to 30 millikelvin as like a log sort of scale. And every power, every magnitude is a whole other level of complexity. So, we can do.
So every factor of 10, right, is really hard.
Yeah. So like our system is a helium-3, helium-4 dilution system. So, if you liquefy helium, you can get to the, our first sort of stage. And that's great. But then, what we can do is we can mix helium-3 with helium-4 and within the system, and then that can further remove energy by the energy that's required to help the helium-4 dissolve in the helium-3. And then it self-evaporates off. We can suck that back out and then repump it through the system. But essentially, it takes more energy to help dissolve those.
Yeah, that's fascinating to me because let's say like what liquid nitrogen is only 70 Kelvin, right? Liquid helium is much lower. And I was like, but it's not nowhere near low as millikelvins or nanokelvins. I was always curious, how did they drive or like drive the heat out that effectively. So you're saying I heard about this kind of like helium-3, helium-4 before, but I think the way you explained it makes more sense now. It's like so the actual the soluting helium-3 and helium-4 is a process that take heat out basically of
Yeah,
the
at this
system.
point you already have to be essentially with like you got your large helium-3, your helium-3 systems brought this thing down to temperature first, and that requires special pumping. And if you look into how cryogenics works, there's different methods, but you can do work expansion of gases, like same as how your refrigerator works. There's a limit to how far that can go, right? But essentially you can do that to a point, and then this idea of the helium-3, helium-4 mixture sort of takes over, where you can then start that system, turn that system on, and that can further lower the temperature. What's really cool is, and this part of our system has been disconnected, but you can further go down lower in temperature by applying a magnetic field initially and turning it off. Because what you can do is, if you've got this this order in the system, you turn it off, the energy that gets consumed in trying to raise the entropy of the system, it just takes that last little bit out, right? But it's all these things you can try to do to get further down. I think our system at one point had the record for the lowest temperature, but again, I'm still learning about a good chunk of this because we haven't got this system up and running yet, and we're working towards it.
Oh, how you even get helium-3? Because I actually I never use it, never heard really like of people using it, like because like usually isotopes are like, oh, helium-4, maybe add one more neutron. How do you remove a neutron from the nucleus? Or is that something that's like synthesized or found in nature? I have no idea how people
I'm pretty
get
sure helium-3 is
helium-3.
more prolific helium. And
I think that's true.
I thought helium is 2-4, no? Like 2 protons, 2 neutrons is the on the periodic table, no?
Googling
I
this
also-
now.
Yeah, so helium-4 accounts for like 99.999
I got it
something %,
backwards,
whereas
yeah.
helium-3 is quite a lot rare.
Yeah, so I was
Yeah.
like, what? Yeah. It's like heavy water is rare, but we can still get a lot of it, right? So I guess helium is a similar thing. Helium-3 must be extremely expensive because like helium-4 is expensive. Like normal helium is expensive, right? And because it's flying off to space and it's leaving our atmosphere.
Maybe I mixed up the
yeah.
the numbers for which one we dilute with, but I know that we've got a two loop system where one of them is piped in from the main supplier for our helium gas, and then the other one's a closed knit, which is the expensive helium. And I may have mixed up my numbers, but I don't remember. This is stuff that like I'm aware of how it works, and we haven't turned this thing on yet, so it's not my area of expertise yet.
Yeah. I guess when you're mixing up, you're losing it too, right? Like unless you can separate helium-3 and helium-4.
You can, because they have different boiling temperatures, so you can siphon one off.
Okay, that's good because you don't have to waste the helium every time you do it.
Yeah, I remember talking to other people in these ultra cold experiments, and helium-4, it's like the less expensive one, and it brings you down to some temperature, and then you hop over to helium-3 to get like to get it lower, but that's way more expensive. And then there's all kinds of different techniques you can do, like mixing them, like you said, and there's other things, and
gets pretty technical pretty fast.
Yeah, back to you said there's these 2 entangled drums. That they were a big thing. So where does your research kind of fit into that?
Well, I'm trying
what's
to
different about it, or what's similar?
Not necessarily the entanglement experiment, but I'm looking to do something similar to what's going on with this. But it's a work in progress. So we're trying to make these sort of resonant quantum systems and incorporate 2D materials, because 2D materials allow for a fabrication that can sometimes be I'm going to say thinner in some respects than say just evaporating like an aluminum, like an amorphous aluminum that's been evaporated from say an electron beam process. That's going to be so thick in order to structurally hold itself, whereas 2D materials are quite strong. in plane, right? So you can have a bunch of the 2D materials or a heterostructure of those and have it as quite a strong, medium to work.
Uh, How do you even get something that's thin? Do you use duct tape?
So, yeah, not quite duct tape. What we typically do in the lab is we have, say, Scotch tape or a less adhesive tape. So we have these low adhesive tapes that we can use on the bulk crystal that separates the crystal into thin sheets. Then we've built a special placement system which involves a microscope and like manipulators, and we can then place them onto microchips where we've fabricated, say, base layers, etc., and then place them exactly where we need to in a desired circuit. So my lab mates, he worked on building a transistor out of MOS2. I've been working on taking these flakes and trying to build them into materials, which are then incorporated into the circuit, and then we, through like conventional lithography techniques, or say, again, critical point drying and things like that, we can try to suspend them to create oscillators. That's one aspect of our work, and I can get into the technicalities how we try to do that. But we also work with, say, decorating these materials and trying to look at, say, what is their interaction of, say, like a plasmon and excitons, that are going on. So we've decorated, say, a MOS2 with gold nanoparticles, which can support surface plasmons, and then we've got MOS2, which has an exciton at a particular spectrum, or sorry, a particular wavelength. And we've done an experiment where we put these particles on it, and we noticed that we get peak splitting, sort of similar to like what you get from like a vacuum Rabi oscillation. So you can apply the James Cummings model, and you can see how the quantum mechanics is happening real time in the light that's being trapped there, and the excitons that are being released and how they're strongly coupling to the plasmons, etc. So you get these really interesting quantum systems that can be developed because this tiny little layer of material is so thin, and yet you've got these other particles that are built around it, and it's all being trapped in this sort of tiny area. But it's all pretty cool stuff. But
Yeah, I remember visiting your lab, right? I think it's quite complicated to even like lift that thin layer out to be able to be used and such. I remember you had quite some time with it, and because I remember when people study graphene and they want to take out graphene in layer at a time, they use like a Scotch tape and just kind of use that as adhesive to take out layers and layers, and yeah, so most of your work is experimental, but I know you're doing computational stuff too to kind of simulate what you're gonna see. Um, can you talk a little bit about that? Like, do you simulate the acoustic drums, or is it like what kind of, or maybe not acoustic, but what's it called the mini drums, or is it magnetic drum, electrical drum, photonic drum?
So the system that we were working with and recently has been a capacitive drive idea. So suppose I have a very, very thin, pliable material that is above an electrode. That thin, pliable material will have an electrostatic attraction to the electrode below. However, we also understand if you apply voltage, this thing acts as a capacitor. So if we hook this thing up to these two, the top electrode and the bottom electrode, if we connect them to a very long inductor, we have an inductor capacitor circuit. Well, inductor capacitor circuits are well documented. We've got a very long resonance frequency. But what happens is, as the pliable top of that capacitor moves up and down, it changes the capacitance and thus changes the resonant frequency. So we can actually track the position of the middle of that drum with really high resolution, depending on the change in the resonant frequency. So great. I've tried to model some of that. I've been working on trying to get this to work. It is a bit of a tricky thing for computers, because if you look up what's easy to model and what's not, apparently the bending of a very, very, very long, very thin, slender beam is a notoriously hard problem. So
it's the I like the deformed material, like the deformed line and such, right? Like,
yeah, we're officially outside of the nice linear zones, and things start to act awful. So that's what we're working with. But what's cool about this idea is if you could pinpoint the position of that to really high precision, the only thing that's limiting you is the Heisenberg uncertainty principle. So you get
wow, so it's very precise.
like this is the idea for all this sort of for at least for my drum work is if we can create these things and map how the change in the resonant frequency is happening, we can measure the position of these drums, and we can make, say, an incredibly sensitive sensor, right? And then through
It
special,
could be like the head of the atomic force microscope or something, right? Like because your drum could be extremely sensitive.
And that's sort of similar to what we're thinking, right? Now they've done this with like aluminum drums, but theirs were 100 nanometers or more thick, 150 nanometers thick. How precise would this, or not necessarily precise, but how sensitive would it be if your material is not 100 nanometers thick, but say like 10 nanometers thick or 1 nanometer thick? And one of the things we were looking to do is say, okay, well, if this thing is limited to Heisenberg's uncertainty, the standard deviation of the motion that's being left over is this 0-point motion. Well, it says that the lower the mass, right, and essentially the thinner this thing is going to be, the effective mass, this thing's going to be moving a lot more. Our goal is to try to, can we measure like this 0-point motion? Can we measure some of these things and put it into a ground state and measure it and start to look at, hey, we just dropped this macroscopic object to a quantum state, and can we squeeze it? Can we do some interesting operations with it? With the goal being, what are our applications way down the road? Well, it could be a really, really sensitive sensor, or maybe it's something where once we can actually read this thing out to a particular position sensitivity, we could be looking at a way to incorporate, say, a quantum state into a piece of physical memory, like through the modes.
Yeah. Any time that you have like a macroscopic quantum state, you can immediately just start listing off like applications for quantum computers and all kinds of things like that, I think.
So I am curious about the actual implementation of these things, and we spent a lot of time talking about cooling and getting it to those temperatures, but can you just kind of walk us through the process of going from something that's room temperature that you've just produced, say, in a nanofab, to getting it to these millikelvin, like the steps that are taken to actually cool these things, and kind of risks, because materials do change as they get colder, and what's the whole, I guess, kind of list in a nutshell?
I'm not familiar with whole cool down procedures yet. I know we've got a book on them in the lab, but I can, the system was looked at by an engineer about a year or so ago who came in to take a look at it and work on it, get half of it up and running, did some tests with liquid nitrogen, but we were sort of on hold because of helium issues. So that part's been put off for the last little bit. So once I'm done working on the sort of side project that I'm working on at the moment, then we're going to be going back into this full tilt, because we've got a helium reliquefier purchased by the department that's just been installed, and then it's, can we source some helium?
Very cool.
Yeah, it seems like there's a lot of moving parts into just making these kind of drums, right? Like there's a material part, there's a cooling part, and because when you make the actual material, like the nano layers or like this, hopefully single layer or a few layers, they're at room temperature. But then you have to somehow cool it later. It's not like you're not making everything at very low temperature, right?
Yeah, we make everything at room temperature and then work from down. So we have Queens is lucky. It has a nanofab facility that's got a lot of interesting equipment in there that you've got. Physical vapor deposition. There's a sputter system. It's an E-beam evaporator. We have an SEM that also works as an E-beam lithography system. There's a maskless lithography. There's a mask lithography system. You've got a lot of really cool things. So
lithography is basically carving into surface, right?
Yeah, so lithography is this act of patterning a surface and then carving into it. Or so what we typically do in the modern sense is we spin coat a very thin film of what you would call a photoresist onto a substrate. Then we expose it with a pattern and we give it a dose of, say, UV or electron beams, or sorry, electrons from an EBL system. And what happens is we change the chemical nature of the resist by this exposure. Then we develop, and by developing, we either remove the part that was exposed or remove the part that wasn't exposed, depending on the type of resist it is. So then we get these, essentially a mask that's on your substrate, or like a stencil. And then you can evaporate metal to it, which will lay down a layer of pattern.
Well, the way I understand lithography is that in art, there's a type of art. Well, I think what's it called? It's not painting. It's called etching, right? Where you have some kind of tar on top of your soon to be art, and then you carve certain part out, and then you bathe it with acid, so it basically corrode out certain part, and once you clean out everything, so you have this nice groove in your what's it called, canvas, and then you're gonna have whatever art, and then and you can use that to print as a what's it called, a mold to print other things. But lithography is basically doing that with light instead of acid, right? And I think lithography are used quite a bit in like try to patterning or printing CPUs or something,
All
or
this.
like this really small scale.
So like right now, we can, you can do it with this resist stuff to evaporate metal on, but you could also have metal there first, do this whole process, and then put it in an etchant and etch away, just like in the art method. Or, to quote how they made one of the greatest films of all time, in the Lord of the Rings, all the armor, what they did is they had people paint on this metal, and then they exposed it to a weak acid, and it etched everywhere that the paint wasn't, because the paint was a protective coating. It's just whenever you want to do things at the nanoscale, it's always a couple steps harder, because it's very difficult to pick up or touch things or paint things that you can only view under a microscope.
And those patterns are tiny, tiny patterns, right? Like,
So
how do you engrave that pattern? Like, even make that pattern? Do they go under microscope and just like carefully carve them out, or is there some kind of natural patterning?
So we precisely do that. So what we do is we expose, a pattern, through essentially a system where the light shines on it, it goes through an objective lens, and it's focused on our sample. And, we can get resolution with some of these things down to, say, half a micron, which is like an optical system, pretty, depending on how well you're doing it. And then we are the EBL system. You can focus even a little more. You can go down to, into the hundreds of nanometers or even the tens of nanometers. Some of the structures that we've been patterning our flakes with, when we, decorate them on the top of nanoparticles, we were patterning little discs that were about, I'm going to say 40 to 50 nanometers in diameter. So tiny little circles that are 50 nanometers in diameter. We were drawing those in nice little grid arrays.
Because I know like computer architecture now, they use lithography to go down to like the single digit nanometers architecture, which is crazy.
Oh yeah, they have way better systems than we have.
So I was thinking that we can change up the topic a little bit for the sake of time. So Nathan, you did a math degree and you became a teacher for a while, and then you decide to come back and do research. So I'm wondering if you can talk about what kind of got you into doing a math degree and then teaching, and then why did you decide to come back? Or can you just comment on it a bit? Because it's definitely less typical for people, I find, doing like engineering or physics degrees. A lot of them just went straight through with high school, and they just kind of went with the flow and then ended up where they ended up.
Yeah, so my fault is that I like to learn and I'm curious. So I did an undergraduate degree at Brock, and I did a Bachelor of Science in Physics with honors degree in that. And I did a teachers college there at the same time. Then I got a job teaching. So I was teaching high school math, science, and a little bit of other stuff out west. And what I did is I applied to do the Masters of Math for Teachers program through the University of Waterloo. Great program. And it was like, hey, here's a bunch of possible courses you could take. It's online. It's an online master's because, you could be anywhere in the world taking this. And it was course based and you'd have a final project. And the gist of it was, well, you take probability in high school. Well, you know what? Your teacher should have a better knowledge of probability. So here's a university course in probability. Or here's a, course in proofs. Here's a course in, differential equation modeling and doing some interesting ways to solve that. I took a course in fractals and some chaos stuff, and I did some other courses in, introduction. I did a computer science course through that. That, believe me, was nothing like the undergraduate computer science course I took. It was really interesting. I really loved what I did, but I realized I was working a full-time job and I was taking courses, and it gets very busy. And I wanted to keep taking courses. So I had to make a decision between, okay, am I going to go back to school properly and do this the right way? Because, is school going to become my job, or am I going to have to just how am I going to do this, right? Should I just teach? Say, okay, it's enough of courses, don't have time in my day. Where do I go back to school?
Right. At the time, I think you started having young children too, right? That also took a lot of your time.
Oh, yeah. So I had young kids, and, I was like, this might be nice in that I can, be around a little more, and gave us an opportunity to also, be closer to family, and gave us a nice sort of combination of things where it's like, you know what, like, I would like to pursue higher education again, properly, and go maybe see how far I can take it, because I had so many questions I'd like to still pursue, and that felt like I had to go back. But it was the time of life where it's like, okay, I'm halfway across the country from where my kids' grandparents would be. So it maybe makes sense if we were going to do a change, that was the time, right? So I threw out some applications, stating what I was interested in, what I'd like to do, and this is where I ended up.
What was it like transitioning from teaching in like high school back into like academia, or like into like a higher education, like being like a PhD student? Was it because like I think all of us here, the co-hosts here, we went from undergrad and right to masters and into our PhD, so we don't have that experience of working outside of it. We are in this box for a long time. But what is it like to be outside of that box and coming back in?
So I do joke about this at times. I tell people that I am the proof of concept, not the desirable model to emulate. It's not easy, although it's got some perks. So for one, I worked a full-time job, so being on the clock X number of hours per day, so many hours per week, doing whatever, grinding it out, you get used to that. So you treat this like your job. You're not likely to slack off the same way as, say, someone just finished their undergrad and they're like, hey, as much as you think you might be putting that full whatever in, like, when you get into the actual workforce and you get people that are there like waking up at 5 a.m. and working until like some late time in the afternoon, you treat it differently when it's your job. And yeah, so it's like when you come back, you got a different sort of mindset. You've also picked up life experience, so little weird things that you would never be able to quantify. Being able to find a screw that is like less than about 2 millimeters tall, less than a millimeter wide, on a floor after it falls. I watched 3 summer students search for 40 minutes and couldn't get it. I go, you guys are ridiculous. It took me 10 seconds to pick it up. I was like, all right, where'd you almost drop it? And it takes me, drop to the ground. I'm like, there it is, done. Like, listen, I find, like, you know how often my kids drop things and you have to like find it? Like, it's all the time. So like weird stuff, you're just able to do it. But like, it's definitely harder because there's you got kids, you got weird schedules. I get kids that are randomly sick, or kids that school calls because they fell off play equipment and you gotta go pick them up because they're like, well, they said their head hurts. You're like, okay. And you ask them, you're like, so you fell? And you're like, yep. And you said your head hurt? You're like, yep. And now? Not anymore. Well, you're home now. So your day is a little bit topsy-turvy at times.
I imagine that.
Yeah, I know,
oh,
yeah.
sorry. I was gonna say. I imagine so. On top of all of that, I would have actually liked to finish my undergrad and go work somewhere for a bit, or do like I think that would be very useful. Again, it has its own problems, but I think especially like I don't know. I see all these PhD students in physics who just can't teach for the life of them. They have no communication skills at all. And going and being a teacher for a while and coming back to academia, I think you'd be way better at communication than many PhD students I know are. I spend a lot of time trying to improve my communication abilities, so it's something I really appreciate when someone can communicate well.
Yeah, you can. I think that there is something to be said for, taking a break, going to work, coming back later. So, but it is a learning curve, right? You have to relearn. You're no longer fresh. So when you don't, imagine giving up coding for 6 months to then pick it up again. You got to get back in the game, right? Imagine doing it for 10 years. It changes everything.
Yeah, well, all the programs would be completely different by then.
Like when I did I did my computer science class through Waterloo. I was like, oh right, we're gonna go to Python or something awesome. No, we did Racket. So and this was even the playing field in case anybody had experience with a previous programming language. But the concepts will still reapply, but the language is completely different. So I'm learning Racket. I'm like, this is the weirdest thing. It was a derivative of Lisp. So if you ever want to look up a interesting computer language, look up an actual functional programming language, because most languages are procedural, where you can give it steps and tell it what to do. This was a functional, where everything must be a function that acts upon it sort of self-recursively. So it was quite the interesting challenge. So
it's kind of weird object-oriented programming, right? So instead of objects, you have functions. You have functions instead of objects, but it works differently. It's like like in group theory, you just work with different groups. And it's like, well, they're groups, but there's programming, but they behave differently, entirely differently. They have their own ways of doing things, and I never did any kind of functional coding, and I don't know if I want to.
Yeah, anybody that knew how to code hates that sort of stuff. They're like, oh, don't want to go near it. But yeah, there's a whole train of thought where people like programs like Lisp. So I encourage all of you to go out and learn Racket, and forget that I told you this, because you'll be mad at me. Yes,
character building.
Yeah, that's what it is.
Yes, let's go back to like Fortran 77 and like see what happens.
Reverse Polish notation calculators. There we go.
Yeah, I'm so glad we don't have to worry about like columns and stuff when we code. It's like so. I'm gonna walk you back down memory lane as we always do in this podcast. So, what made you interested in the science domain in the first place? Was this always something that you really like when you were young, like like since you were like little? Or was that interest came later on in your like maybe in high school, or maybe you like did you go into science knowing you wanted to go into science? Like what was it like in terms of like your beginning, your origin story?
I've always loved math and science. My biggest thing was always how you could write an equation, do some theory, do some idea, and then nature would behave according to that. Or that you could take a series of measurements and map it to a well-known theory, right? And you can predict things with this. That to me was always such an amazing phenomena. So that drew me in, and that's I sort of hugged the line between experimental physics, and I enjoy my math with it, right? Because you can do some pretty incredible modeling, and there's some pretty interesting theory that goes along with the stuff that I'm doing. It's not so much like you take a few measurements, you supply X theory, and it's done. It's more like, what can we do? Can we model the system? Can we do this? Because there's actually a fair bit of computation that goes along with it, right? So it's a really interesting meshing of the two, loving the math and loving the how the real world behavior agrees with it.
I figure when we were young, or I mean when you were young, the computer modeling wasn't really that prominent. Especially when we were young, we didn't know that much about computer modeling, right? When we learned science in elementary school or even middle school, high school, computer modeling is not really taught. At least to me, it is more like here's a theory, this is physics, right? And yeah, so without even the modeling part, you are still like to do science and math then, like, but because I guess the modeling or like computer parts comes later on.
Yeah, for me, it was just, a few analytical equations. How can we best describe this? Can we fit it? There's obviously going to be some deviance, but is it within certain, mostly there, right? Can you, how well does, say, a pendulum's period follow its length, right? Or can you map out, say, gravity, a constant value from that? Like for me, that's a pretty incredible thing. If you can take a series of measurements and show this is what some constant that's fundamental to nature is, right? That's a pretty crazy thing for me.
Yeah, I think basically the scientific history itself is pretty fascinating, and maybe math is even crazier because you don't even see it, or the geniuses, or they just see it. They just say, "Oh, it's true." How do you know it's true? It's true. It's so obvious, isn't it?
Well,
and
one of the things that I've been working on for the last couple of days here is, in a lot of the papers, this has been done, but I'm doing a slightly different derivation for our particular set of circumstances. But if you were to take a substrate, some material, and you were to look at its reflection spectrum, that's great. You can look at that and say, cool, here's a spectrum. If you put a very, very thin film on that of a different material and then measure this reflection spectrum again, well, what you can do is you can subtract the two. You'll see the tiniest bit of a shift. It just so happens that the difference of the two divided by the original substrate reflection is related to the absorption. And from that, you can actually, if you have, say, a model for the dielectric function, some Lorentzian model, for example, what you can actually do is, for the most part, you can, depending on your set of circumstances, you can map out the dielectric function of a material from just looking at the reflection of a substrate versus the material on that substrate. So being able to find something like its dielectric constant for all the different wavelengths that you've observed, that's a pretty crazy. You just looked at how this material responds to electric fields by looking at it.
Yeah, a lot of modern discovery or like modern measurement is basically a roundabout way to get specific thing, right? Like, it's not like back in the days, like what do you want to find? Mass? Just measure the weight divided by gravity. This is pretty straightforward. But now it's like, you want to have this constant, or you do this 10,000 things, and you have a chance to get this into somewhat this precision. So I'm gonna pivot this into basically the last question we like to ask our guest, which is the hopes and dreams. And so this question is about, who do you see yourself being? I'm not asking about like 10 years, 5 years. There's no time frame, but do you see yourself being like a professor? What type of scientist you want to be, or who do you see yourself being? What exactly are your hopes and dreams? It's a loaded question, but this is a loaded podcast.
Well, I'm thinking about my wife wants me to do something in industry, and I think it'd be good to do something in industry for a little bit. Whether that be, finding a job as a nanofab person that does, helps make some of these devices come to fruition, because you need somebody not only to physically do the processes, but to do the math and to help you develop your, say, special meta surface or whatever you're making, or your special, all these different little things to do with the lithography. So there's a lot of technical skills. There's also a lot of the developing it. So there's a big push right now um, for, I was going to say local, but not quite local. It's sort of semiconductor fabrication that is not made half a world away. So you still need people to help test out the fab processes and be able to do some custom stuff here on the side. Besides, the big official. Here's the official run sheet, which we send to the robots in an ultra clean lab to mass production. There's still a lot of test stuff that happens. So maybe a job like that or something, but maybe in the end, I don't know, maybe do something in a professorship or something, but that would be, I feel like it'd take things a couple of years at a time. So for right now, I'm still leaning into some sort of industrial or science job, and then we'll see where it goes.
So you like a practical side of things too,
Yeah,
right?
I like the practical, but I think it's like I do enjoy the science and the figuring things out and think about IBM. IBM had guys working on this stuff for years, right? So they were working on all these different fabrication processes and all these different, can we make this? Can we make a thing that does that? Can we make a chip with this? So they have the whole research divisions that do a lot of this stuff. And it's pretty exciting work they do. So there's that. I don't know. I think it's dependent. We live in an interesting age when what used to be true is no longer maybe true. If we look at what could you look in the future and tell me what the future of nanophotonics and the semiconductor industry is going to look like in say 20 years? Is Taiwan still going to be producing all the chips, or who's going to be making what where? Like, we don't know, right?
Yeah, it could be Canada.
Could be Ohio. Right now, what's scary is all it takes is one geopolitical event, and all those high-end chips would be gone. So,
Well, I mean, yeah, nobody knows about what future is gonna lie ahead, right? And it's good. I mean, you're kind of hands-on kind of guy, so I think you do working and stuff too, if I remember. And yeah, we need people to actually sit down or stand up and actually do stuff with their hands, because theorists like me and Liam, we can't really prove things. Well, we can prove things on paper, but what matters is what can be proven out there.
I find what's neat is the theory guys can come up with some really cool ideas, and they can do some of the really cool math that you don't have to always be working on, because the actual fabrication sometimes is so disruptive on how many times it's. So I find what's neat with the theory guys is, you guys are really fresh with all the theory. You guys can work stuff out and you can come up with these solutions in terms of the math, but we get held up a lot with the fabrication protocols, trying to get these things to be fabricated in such a way that they work. But then we still have to go back to the theory, and we do a little bit of theory on our own on the side, but it's, we do rely on you guys a lot, but it's difficult that you can't just omit some of these factors. Sometimes you can't just say, oh, that phase out, we won't worry about that. Well, we need you guys to justify when we can not worry about it and when we can worry about it. And sometimes you guys know all those extra, like the guys that do theory just all the time, know all the extra shortcuts and all those Bessel integrals that we all forget. So we rely on you guys a lot.
Yeah. Well, from what I've seen, it's like some theorist, 50 years ago or something, comes up with some minimal model, toy model thing. And then experimentalists spend a long time trying to figure out how to get that. And then they realize that, okay, there's all these limitations. And then the theory people come back and do a theory. They take that original toy model and then build on these extra kind of limitations onto the theory. And then the experimentalist
yeah,
get
it's
something
like
that matches that.
You come with a
Or
theory
not.
as like how cows work, and all the cows are like spheres, and you can either amend the theory so cows are more like cows, not like spheres, or get the experiment to be like make cows more like spheres, and which one is harder? And sometimes it's the cows making to the spheres easier, and sometimes it's amending the theory. So it is kind of trade-offs. But yeah, I think it's been a great discussion, but in interest of time, I think we should cut it here unless anyone has the last comments or so. Yeah, but thank you, Nathan. I think it's been great, man, having you up here. Well, up here, but yeah, in here.
Thanks for having
Good
me.
to hear what you what your work is and your story. It's been great. So before we move on, we will we will get Patrick to tell you guys how to contact us and where to find us. And then we'll end up with a story.
Yes. So if you are interested in being a guest on our show, much like Nathan, and we are very thankful for Nathan for coming on today, you can reach out to us several different ways. So we have an email. We are hyperthesispodcast@gmail.com. You can send us an email with questions or comments. Or if you have questions for Nathan, you can send it to us. We'll send it to him. Or Nathan, do you have a way in which you'd like people to contact you or not?
I think Pheely can relay it all to me. I know where he lives and he knows where I live, and yeah, it's all
Perfect.
good.
So if you do have questions for Nathan, send them to hyperthesispodcast@gmail.com and we will relay them to Nathan. You can also find us on Instagram. We are at the Hyperthesis, where we are posting updates. So we are recording early. We are technically on a break right now just from posting. So you can check out our Instagram where we post updates during our breaks as well as when we start things again. And you can get some interesting insights into the podcast as well. You can send us a direct message on Instagram, or you can just like and follow us, subscribe. I forget what you have to do on Instagram. If you are listening to us, congratulations, you found us. If you would like to share us, we are on pretty much whatever podcasting service there is, whether it's Spotify, Apple, Google, Amazon, where we are on all the podcasting services. And we are also on YouTube. So we don't actually have videos of our episodes, but we do have these cool animations that Pheely has worked on, and each season is a little bit different. So make sure to check those out. Give us a like and subscribe and a share there. And again, if you have any questions, contact us through any of our means, and make sure to give us a follow or a subscribe.
All right, so today's story gonna be done by your truly's Liam.
Hello. So today's story is going to be a very, very, very condensed history of nanotechnology, which we heard a lot about today. So, as we didn't explicitly say this, but we alluded towards it, that nanotechnology is defined as technology that requires the manipulation of material on the nanoscale. So, 1 to 100 nanometers range, or a little smaller, a little bigger. It kind of depends who you ask. And for reference, the diameter of a hydrogen atom is about 0.1 nanometers. And at these small scales, like we talked about, surface effects, surface area effects, topological things, and quantum mechanical effects become quite important to understand the system, and you often can't neglect them. And nanotechnology as a whole, when I say nanotechnology, it could mean a lot of things. It's this extremely wide range of fields, or it's this extremely wide range of different branches that people study. And we heard about Nathan's research today as one example, but semiconductor physics is another big one. Quantum computers, energy storage science. There's medical applications like drug delivery, and there's molecular engineering. There's all, depending who you talk to, they could have a completely different concept of nanotechnology in their head, or a different way to think about it. The original concept of nanotechnology, it was first discussed in 1959 by the famous physicist Richard Feynman in one of his talks titled "There's Plenty of Room at the Bottom." And in this discussion, he described the possibility of the direct manipulation of atoms in order to synthesize certain molecules. I'm not quite sure how much he got into it, but that was kind of like the seed for the idea of nanotechnology. And even if he hadn't talked about it, people would have figured it out on their own, no problem, I think. But that's the first kind of modern day record of it being talked about. Interestingly enough, nanoparticles were actually around long before Feynman proposed that idea. whether or not people knew about it at the time, they were in pottery. A lot of ancient pottery had nanoparticles on its surface for some reason. I'll tell you why. Um, the first example is that carbon nanotubes have been found in Indian pottery from around 600 to 300 BC, though the details of their formation and whether or not they were intentionally created is unknown. I'm going to guess they weren't intentionally creating carbon nanotubes for their pottery, but who knows? There's also nanowires have been found in this Damascus steel, which is this special form of steel that dates back to around 900 AD. And again, we don't really understand how it got there or if the people putting it there knew it was there. But one application we do know about is that in the Middle Ages, nanoparticles were used to create this glittering effect on the surface of pots. So nanoparticles were created by potters by adding copper and silver salts and oxides together with vinegar and different types of clay, and they would apply that to a previously glazed piece of pottery, and it would give it this really nice shine. And the reason why they did this is because this technique originated in the Muslim world, and Muslims weren't actually allowed to use gold in their art during that time. So they had to develop a way to make their pots shiny without using real gold. So whether or not they knew about nanoparticles, they were actually creating them and applying them for decoration purposes. The actual term nanotechnology was first coined in 1974 by the scientist Norio Taniguchi, which I may have pronounced wrong. I apologize. And he proposed it in 1974, but people didn't really come to know about it for a while. It kind of sat there dormant in some of his publications for a while, until about 1989, when the engineer K. Eric Drexler used the term nanotechnology in a book that he wrote titled Engines of Creation, The Coming Era of Nanotechnology. This book tackled the idea of nanoscale assemblers, which could be used to build a copy of itself and create other small complex items using atomic control. And nowadays, nanoscale self-assembly is a whole branch of science, it turns out. So he had some idea of what he was talking about for sure. And Drexler also co-founded the Foresight Institute in 1986. He's no longer affiliated with this for some reason that's unknown to me. I just wanted to point that out because when I was looking this up, the articles I read had they really made a big deal out of the fact that he wasn't affiliated with this place anymore, and I don't know why. But anyway, he helped found this Foresight Institute, which the goal was to help create public awareness and increase kind of knowledge of this rising field of nanotechnology. Drexler's theoretical and public work definitely helped develop and popularize nanotechnology, along with some new experimental advances that drew attention to the prospects of atomic control of matter. In the 1980s, there was some major breakthroughs that caused kind of this huge growth in nanotechnology interest. The first was the invention of the scanning tunneling electron microscope in 1981, which enabled the visualization of individual atoms and bonds, and it was successfully used to manipulate atoms in 1989. And this won a Nobel Prize. We've talked about this before, I think. I forget which episode, but we've definitely talked about this microscope and the Nobel Prize surrounding it. It might have been the guest episode with Kat. Another discovery that was pivotal for nanotechnology was the discovery of fullerenes in 1985. One popular example of a fullerene is C60, also known as a buckyball, which some scientists might have heard of before. It's this kind of closed mesh of carbon atoms connected by single and double bonds, and this also won a Nobel Prize in chemistry. And then the discovery of carbon nanotubes, which listeners may have heard of before, and which I talked about being in that Indian pottery. That was also a huge deal because they have lots of applications, which I'm not knowledgeable enough to comment on, but I know they do. When you scroll through the archive, there's a few publications popping up every now and then on carbon nanotubes, and they have a lot of application in chemistry as well. So the discovery of carbon nanotubes won a Nobel Prize. So these were some big ones, but kind of after the 80s and 90s and early 2000s, nanotechnology really had this kind of huge increase in popularity. In the early 2000s is when it really kind of started getting more public knowledge. It gained a lot more political and commercial attention that led to some progress and some controversy. So a lot of questions emerged regarding kind of the definitions and potential implications of nanotechnologies. And concerns kind of were raised about the feasibility of the applications and their impact on the planet. But despite this, people realized they could make money off of them and took all those concerns and tossed them in the bin. So they realized that you could really make money off of these things. So the commercialization of products based on advancements in nanoscale technologies began. And some examples include people started using silver nanoparticles as antibacterial agents. There was nanoparticle-based transparent sunscreens companies produced, carbon fiber strengthening using silicon nanoparticles, and again, people actually used carbon nanotubes to create stain-resistant textiles. Governments eventually decided to promote and fund nanotechnology because once they realized kind of its huge potential. And in the US, the National Nanotechnology Initiative was formed and formalized. They formalized a size-based definition of nanotechnology and established funding for research on the nanoscale. And in Europe, something similar happened with the European Framework Programs for Research and Technological Development. So by the mid-2000s, there was a great deal of scientific progress in nanotechnology and attention made regarding how much potential it had. And currently, there's so many different subdivisions of nanotechnology, I can't even begin to list them here. But we were lucky enough to hear from Nathan today what he did and his research in the field.
All right. Thank you, Liam, for the story of the nano stuff. So, all right. I think that brings us to the end of the episode. Thank you, Nathan, for coming in. And I'll see you guys later. Take care.
Thanks for having me.
Bye, everyone.
See you guys. Thank you.
Yeah.